Hey and welcome. Today we are going to solve leaf similar trees interview question. So let's get into it. First example here, we have this tree and then this tree right here. If we compare all the leaf nodes in both subtrees from left to right, they have same value and are in the same order. It actually doesn't matter which breadth they are. Like this child nodes of 7 and 4 here. The only thing that matters is if we look at leaf nodes from left to right, they are in the same order. So that is why we return true for it. This is more obvious in the next example where we have 2 and 3 in the left subtree, but we have 3 and 2 in the right one, and we return false for it because they are not in the same order. Let's see how we are going to solve this problem. Okay. Before we get into this, please pause the video and write in the comments that what tree traversal solution came into your mind first. If you have guessed depth first search, then great, because that is what we are going to use. But if not, I have short videos for both DFS and BFS that you can watch. So please refer to them if you need to refresh your mind about the topic. Okay, enough of advertising my videos. Let's get into the point now. The problem itself points us about the leaves of each subtree, and the only fastest way that we can reach into the leaves of a subtree is obviously depth first search. Let's analyze this problem for a bit. Here we have the trees from first example. We know how to reach the leaf nodes in the given tree, but how we are going to compare them, that's the problem here. Well, since the leaf nodes can be in different breadths for each subtree, we cannot really trust on the results of doing a simultaneous DFS on both subtrees. Because for example, the 7 here exists in this level in the right subtree, but still both of them are leaf nodes. That is one important observation here. But to overcome that issue, we need to store leaf nodes from each subtree somewhere to compare it later. For that, we are going to need a simple array or set. Honestly, you can choose either of those that you are more comfortable with, since both of them are super easy to code up, but I'll show you the array solution without any extra addition on the time complexity, and we will keep it to O of m. So as a brief overview of what we came up with, the solution would be to have a DFS helper function that goes deep into the given root node path and stores the leaf nodes values into an array, and keep doing this iteration until we are done with the DFS process. Then later compare resulted leaf node arrays values, and if they are same value and also have the same order, then return true. Let's jump into the code to implement this. First, we need to create our arrays for leaf nodes of both subtrees. So 2 arrays we need, and I'll call them storage 1 and 2. Then we need to implement our DFS function, which will receive a root node to process, plus the related storage array to put the leaf nodes values into it. Okay, first things first about the DFS function. If the given node is null, we might return, because presumably this null node is either left or right child of a leaf node, so we don't want to process it. Then think about how we can figure out if the given node is leaf node. It is when that node does not have any left or right child. That is the time when we are going to push it to the storage. And finally, again, the routine for a decent DFS function, recursively call DFS on left and right child, but note that we will pass the storage along with that call as well. Okay, we are done with the DFS function. Now it's time to call it and pass the root nodes of 2 subtrees to fill up the leaf nodes array for us. Note that our DFS function does not return a special thing. We just invoke for each root node and pass the related storage array to it. It just fills those storages with leaf nodes of that tree. And here it comes the time to compare values of those subtrees. One obvious thing is that after processing both trees, if the lengths of our storage array are not the same, then we are done, right? We have our answer of false. So first we are going to check for lengths. But if they are equal, we need to compare values, and for that we will use the every method on JavaScript arrays. It will help us to compare values one by one, and since by now, based on our lengths comparison, we are sure that both arrays have the same lengths, then we can leverage the second argument that it provides for us as an array index to directly access the values in the same index from the other storage to compare. And obviously, if any value is not in the correct order or has different value, the every method will will return false. Otherwise, it will return true as our final answer. Now, if I run this, test cases are passing, and if I submit, we are in a good shape here. Let's jump into the slides to analyze the time and space complexity. So the time complexity will be O of sum of the time it takes to process nodes in both trees. The reason for it is simple, because first we need to process each subtree individually to reach to the depths of every possible tree path from root node that we have. Plus, we are not sure if the subtrees are going to have same breadth count. One could be 2 levels deep, the other could be 5 levels deep, but with the same leaf nodes. And that is why the time complexity will be the sum of time that it takes to process both trees entirely. The space complexity will be O of n plus m because of color stacks. N and m here represents the length of the trees. So that was it for this video. Thanks for watching, and please leave a like, comment and subscribe to the channel. I will put a few more links about different playlists in the description for you to check it out. And finally, hope you enjoyed this video and stay tuned for the next one.